Imagine a hacker sitting thousands of miles away in a cafe, types few commands, and the city loses power. No explosion, no physical break-in, just bad code. This is not a science fiction. This is actually happened. And it happened because the engineer who builds that system didn't think like hackers. Hi, my name is Mohammad Rizwan, and in the next 10 minutes, I'm going to show you exactly how to think like hackers and so that you can build your system that don't break the way they did. We are talking about cyber physical system, the software that runs power grid, hospital devices, factory floors, self-driving cars. The code we write isn't just the software, it's the infrastructure. It supports life. By the end of this video, you'll understand 6 core security principles, the real mistakes that cause real disaster, and a checklist you can implement in your next project. Stay with me, this one really matters. Let me ask you something. What's the difference between a bug in a social media app and a bug in a pacemaker? The answer is simple. One crashes your feet and the other one could stop a heart. That is the word of cyber physical system. These are the system where code reaches into the physical world and make things happen. Not on a screen, in reality. A SCADA systems opens a valve, a PLC tells conveyor to stop, an insulin pump delivers 5 milligrams of medicine, and a self-driving car decides not to brake. In each case, there is a microprocessor that runs code, and that code either decide the thing in a right way or it doesn't. There are four major domains. The one is the industrial control, the smart infrastructure, the medical devices, and the autonomous vehicle. These are the system where the cyber physical system makes impact. And here is the uncomfortable truth. Most of the software were built before cybersecurity was a priority. The gap between how these systems were designed and how they are being attacked today is exactly what we are here to close. Now let's start the core 6 principle of secure coding in cyber physical system. The foundation that everything else build on. The first principle is least privilege. Every software component should only have the minimum permission it needs to do it. If a sensor reading module doesn't need to write to storage, don't give it write access. If a process is compromised, limited privilege limit the damage. The second one is defense in depth. It means that layering your security. Don't rely on just one mechanism. Use firewalls and authentication and encryption and monitoring. If one layer fails, other catch the attackers. The third one is input validation. It's very critical in cyber physical system. Each sensor reading, every network packet, every user command should be checked before being acted on. A malfunctioned sensor value could command an actuator to a dangerous state. Fail secure is the fourth one. It means that when something goes wrong, the system defaults to the safest possible state. If authentication fails, deny access. Don't skip it. If a valve control signal is lost, close the valve. Don't open it. The fifth one is cryptographic integrity. It means that you sign your firmware, encryption of your communication, and authentication of every command. Finally, the last one is minimize attack surface. Disable every service, every port, and each interface you don't actively need. Even open interfaces is a door for attacker that can be used to enter or walk through into your system. Communication security is a unique challenge in cyber physical system because these systems often use specialized industrial protocol that were not designed with security in mind. Let me walk through some important one. MQTT is used in IoT and industrial systems. Use, or you can say always run it through TLS 1.3 with client certificates and enable access control list to limit who can publish or subscribe to which topics. The other one is Modbus. It is a classical industrial protocol with no built-in security. You must wrap them in VPN tunnels or TLS or add authentication in the application layer. CAN bus is used in automotive and industrial systems. It has no authentication by default. Use AutoSAR secure onboard communication, which adds a message authentication code to each frame. For Bluetooth low energy, use low energy connection mode that provides key exchange. Disable the legacy pairing mode, which vulnerable to brute force attack. Telnet FTP are the plain text. Replace them with SSH or SFTP immediately. There is no justification for keeping them in production cyber physical system. Finally, the most important one is the architectural principle, network segmentation. Your cyber physical system control should be physically and logically separated from your corporate IT network using VLANs or ideally unidirectional gateways, also called as data diodes, that allows data to flow only in one way. Even well-defined systems encounters error, and how your code handles these errors determine whether a failure is recoverable or not. The golden rule is never expose internal state in error messages. Don't return stack traces, memory addresses, internal variable name to users. These helps attackers map your system. Return a generic error code instead and log the detail internally. Define safe fallback states for every possible state or every possible failure. What happens if the network goes down? What happened if sensor stops sending data? Every failure should have been documented and should be tested and should have safe default state. Use hardware watchdog timers. For logging, always use remote secure information and event management system. Not just the local one. Save your logs remotely, because if any attacker temper the local logs or erase the local logs, it can't remove the remote logs. Look at the example log format on the screen. It contains the timestamp, event type, source ID, username, user ID, and the number of attempts and the action taken. These give you everything you need for the forensic analysis after an incident. You don't have to define the security requirement from scratch. There are established international standards for every cyber physical system. IEC 62443, the most comprehensive standard for industrial automation and control system. It defines the security level like SL1 to SL4, and it is based on the capability of the expected hacker. Most critical infrastructure project requires compliance with this standard. ISO SEE 21434 is automotive cyber security standard. It covers entire vehicle life cycle from the initial design to commissioning, and it requires threat analysis at every stage. IEC 64351 is specific to power system and smart grids, covering communication security protocols like IEC 61850 and DNP3. NIST Special Publication 882 is the US government guide for industrial control system security, and it's freely available and excellent starting point for integrated cyber security programs. The FDA's 2023 cyber security guideline mandates that the medical device manufacturer provides a software bill of material SBOM, a complete list of software components in the device, and demonstrate that they have performed threat modeling. So here's the practical advice. Choose the standard relevant to your domain. Map your controls to it early. Many of the standards overlap significantly, so well-structured security programs cover multiple frameworks at once. Testing your security is not optional. You must actively try to attack your own system before real hackers do. There are different type of testing you can perform on your system. First testing, static analysis, red team exercise, penetrating testing, hardware in loop, and formal verification. You should perform these testing on your system before making it into the production. Let's bring it all together. In cyber physical system, security is not a feature you add on the top. It's the fundamental property of the system. A security failure in cyber physical system is also a safety failure. The physical world can't be rolled back with a software patch after an incident. There are four principles to take away from today. The first one is validate everything. Never trust any input no matter the source. The other one is encrypt always. Protect data in rest and motion and authenticate every command. The third one is fail safely. Design every failure mode to default to safest physical state. And the last one is test continuously. Security must be actively verified throughout the development life cycle. These standards we covered: IEC 6443, ISO 21434, and the others give you framework so that you don't have to start from scratch. If you take one thing from the presentation, let it be: build security in, not on. The cost of fixing a security vulnerability after a cyber physical system device is deployed in the field is order of magnitude higher than building it correctly from the first time. And in some cases, there is no fixing it because the harm has already been done. Thank you for your watching. Questions and comments are welcomed.